Hi, in this video we are going to talk about first mathematical tool to represent order of growth of a function, and this tool is called big O notation. Big O notation represents an upper bound on order of growth, and there exists a direct way to find big O notation of any function. The direct way is ignore the lower order terms, ignore the constants of the leading term. Whatever you get is your big O notation. Let's deal with some examples. Say our fn is 3n square plus 2n plus 100. We ignore the lower order terms. This is the highest order term, so we ignore these two. We ignore the constant of highest order term. So we have only n square left, and we say fn is big O of n square. Let us do one more example. This is the highest growing term. We ignore the lower order terms, ignore the constant of the highest growing term, and we say it's big O of n, because n is the only term remaining. So this is a quick way to find big O notation of any function. We have seen a quick way to find big O notation. Let us now see mathematical definition of big O notation. This mathematical definition can be useful to prove that the big O notation that we found is correct. The definition says that we say fn is big O of gn if and only if there exists constants c and n naught such that fn is smaller than or equal to c of gn for all n greater than n naught. What we basically mean is we want to find a function gn which is always going to be greater than or equal to fn when multiplied with a constant and when we talk about large values of n greater than n naught. Right? So we say that c of gn always greater than or equal to fn for all n greater than equal to n naught. Please note that we have equal to sign. So upper bound does not mean exactly higher order of growth. It means equal or higher order of growth, right? And the examples that we did, they were finding equal order of growth. And big O, please remember, covers both equal order of growth and higher order of growth. And soon we'll see what is the point of having two things in one notation. We'll talk about this with some practical application later in this video. So let's see with this definition, let's apply this definition for this function. We have fn equal to 2n plus 3, and using our direct method, we can find out it is big O of n. We ignore the lower order term, we ignore the constant, and we have only n left, so we say it's big O of n. Let's see how is it mathematically correct. So this fn has to be smaller than equal to c of gn for all n greater than equal to a value n naught. Now this fn is 2n plus 3, and we want it to be smaller than c of gn. So what is gn? Gn is n, right? Big O of gn is big O of n here for all n greater than equal to n naught. Now how do you find the values of c and n naught? There is a quick way to find out the value of c, a direct way. You can simply take the constant of highest growing term, which is 2 here. See, the highest growing term is n. If I take more examples, say 3n square plus 4n plus 5, the highest growing term is n square and constant of highest growing term is 3, right? So I simply take the constant of highest growing term, which is 2 here, and I can have c as 2 plus 1, 3. Just take the next integer of constant of highest growing term, which is 2. So we can always safely take c as 3. It's always going to give you a valid n naught. So now we have found c equal to 3. We need to find n naught. So what we do to find n naught is we put this value of c in our expression, and we find for what values of n greater than this n naught we have this condition true. So let's put c equal to 3 in this expression. we are going to get 2n plus 3 is smaller than or equal to 3 of n. And from this we can say 3 is smaller than or equal to n. So this condition is true when n is greater than or equal to 3. So we have found an n naught, right? So now n naught is 3. So when n is greater than or equal to 3, this condition is true. After n naught equal to 3, for all values of n, 3n is going to be greater than or equal to 2n plus 3. You can try putting some values. If you put n equal to 4, you will see that this is greater. 3 into 4 is 12, 4 into 2 is 8, 8 plus 3 is 11. 5 into 3, 15, 5 into 2, 10 plus 3, 13. So when n is greater than or equal to 3, this value is always greater than or equal to 2n plus 3. So we found an upper bound on the given expression. To find an upper bound, we found C and n naught. So our expression for big O that we wrote, that we guessed initially using direct method is correct. Here is pictorial representation for the same thing. We have our function as 2n plus 3. We found C of gn, which is 3n, and this is the line for 3n, this is line for 2n plus 3. And you can notice that after n naught equal to 3, this value is always greater than or equal to fn. Right? So this is our big O notation. This gn is actually our big O, which is n. So big O notation simply represents order of growth. Constants do not matter. Lower order terms do not matter in big O notation. There's no point writing the lower order terms. There's no point writing the constants. There's no point writing big O notation like this. You know this term is lower order term. You can always ignore this. This is equivalent to big O n square. Let us take a look at more examples to get better idea of big O notation. Please remember, whatever we put in big O notation is having same order of growth or more order of growth. So all the expressions, all the functions which have same order of growth, like n by 4, 2n by 4, n by 100 plus log n, if you see all these functions, their order of growth is n. Highest growing term is n. Here also we have big O of n. So they all come under big O notation. Not only this, the expressions or functions which have order of growth less than n, they also come under big O notation. So this is a constant term 100. We can write this also as big O n. You can write even log n as big O of n, or maybe log n plus 100 under big O of n. So big O means equal or more. Whatever you put in big O is equal or more, and it represents the functions which have order of growth equal or less. So log n plus 100 also belong to big O of n. Right? It can also be written as big O of n mathematically. Although it's never a good idea to write a higher growing term in big O notation. If you know it's log n, right? Why would you write n or n square? Although you are mathematically correct, you will find C and n naught for which it will be true, but in general we should be writing the exact order of growth, right? But we'll talk about application. Why do we cover our? I think you must have guessed also. It's because of the worst case, best case and average cases. If you've not got it now, we'll talk about this. Let's see the functions that come under big O of n square. So if you see all these functions, they have highest growing term as n square. So they all come under big O of n square. And mathematically we can say all the functions which are written here, they also come under big O of n square. They are also part of big O of n square because they have order of growth less than n square. All the constant values, they come under big O of 1. It does not matter how big is your constant. As long as it does not depend upon n, it's big O of n. Even if it is this big or bigger than this. If it is a constant, it's big O of 1. So these constants, they also come under big O of n square, big O of n, because they have lower order of growth. Constant means the least order of growth. It does not grow at all in terms of input size. All these things, they come under big O of 1. They also come under all big O notations as well, like n square n, because this is the least order of growth. Let us take a look at this example to get an idea how big O notation can be useful. This is a function to do a linear search in an array. We linearly compare a given element x with every element array I in the array. If it matches, we return the index at that position. If it is not found after traversing the whole array, we return -1. Now, what do you say about the time complexity of this function? What do you say about the order of growth of this function? If you see this function, what might happen sometimes is, if your element is always at the first, second, third positions, this algorithm quickly finds it. But if your element to be searched is not present at all, it's going to traverse through the whole array, and then it's going to decide that the element is not present. So we know in worst case what happens. In worst case, you need to traverse through the whole array if the element is not present. And how much time it takes in worst case? It takes linear time, because you will be comparing x with every element, then you will reach at the end, then you will decide it's not present. So in worst case, the order of growth is n. Now, if you want to represent the time complexity of this algorithm, we can say big O of n. It covers everything. It means the time taken by this algorithm grows linearly or less than linearly. So it covers the best case, it covers the average case, it covers everything. Because we have just taken the worst case into consideration, and we have put the worst case order of growth in big O. And big O definition itself says equal or less, right? So order of growth of time taken by this is going to be growing linearly or less than linearly. In general, when we talk about algorithms, we are mostly concerned about the worst case. We've talked about it. Worst case is the most important case we talk about. So what you do in general, you analyze the algorithm in the worst case. You do not care how much time it takes in the best case or average case. You just find out the order of growth in the worst case. You put that order of growth in big O notation, and then you say that's the time complexity. Because big O covers everything. Big O means an upper bound, right? So it covers the worst case, it covers the best case, it covers the average case. So you are mathematically correct. Even here we are mathematically correct when we say big O of n. Even if it takes constant time for most of the inputs. For example, if your environment is such where the elements are always present at first 2-3 positions, even if it is constant, you are mathematically right, because big O of n covers constant as well. It's an upper bound. We are going to talk about 2 more notations in the upcoming videos, but big O is the most used notation. Why? Because we care about the worst case. We analyze the algorithms generally in the worst case. We find the order of growth in the worst case, and we put this order of growth in big O notation. And that's how we analyze algorithms most of the time.